What's up, guys? We're going to go over the solutions to this interactions worksheet. Bear with me. I'm going to try to change up some of them. Some of them are a little funky, so we're going to take a look at that. Just bear with us as we go through here. So, first example, or first problem, explain what a normal force is and give an example. So normal force is the force exerted by a surface. We've talked about that before. It's always perpendicular to the surface on an object. For instance, a boy sitting in a chair has three normal forces acting on them. The floor pushing up on the feet, the seat of the chair pushing up on his on your bottom and your legs, and the back of the chair pushing their back forward. So when you're sitting in the chair, there actually are three normal forces, three surfaces that are contacting your body. So that's a good example of the normal force. Can inanimate objects such as a table exert a force? Can the magnitude of an inanimate object change? Yes, they can exert forces. A book set on a table pushes the molecules close to the surface, closer together, and then those tiny kind of springs, the atoms kind of push back. The molecules push back on the book until they've balanced the weight of the book so that it doesn't, crash through or break the table. If the book is set on top of the first book, the molecules get pushed even closer together. More weight, they get pushed closer, so they push back harder. This spring-like force of molecules pushing perpendicular surface is known as the normal force. So this normal force can change related to how much reaction it needs. So more books, the table will push more until you get to, based on the material, a breaking point. Obviously, if the lab tables at the school, we tried to place an entire elephant on top of one, it would break. There's always a breaking point based on the materials and how tightly they are bound together, those molecules. So looking at it from a molecular perspective. If an acceleration of an object is zero, are no forces acting on it. The sum of forces is known as a net force, is zero. So sum of forces is known as a net force is zero. There are many forces, but they must add to zero if the object's not accelerating. So accelerating means a net force of zero, meaning there is an unbalanced force, in other words, in a certain direction. Example, a girl standing on the ground has two forces acting on them, the earth pulling her down and the ground pushing her up. When the forces are added, the up plus the down, since they're in opposite directions, they add to zero. That means that there is no acceleration, but that doesn't mean there's no forces. All right, getting to the force diagrams for A and B, I'm going to kind of notate this a little bit with which one's A and which one's B and that kind of thing. You can tell based on the normal force A on B, and that's the kind of notation that they're shorthanding here. And a little bit different than what we've been doing, like spelling it out or whatever, but I think now is the time we need to start shortening it so we can get through this stuff a little bit better. So this is for block A, and these two over here are for block B, and they explain why they have two here. But let me just go ahead and give you an example of what's going on here. So for block A, we have the force of gravity on A by the earth, that's A, comma E. All right, and then we have the force of block B supporting block A, so the force of A on A by B pushing up is the normal force. So that's that box A. Still net force equals zero, no acceleration, no velocity, no nothing, right? Just sitting still, simple example, and those two forces are equal. Now this was drawn in two different ways to show you basically the force acts on the box B, but to show you that these two added together equal the one up, they show it in two different ways here. But forces on box B, we've got gravity. That's this one that you kind of blocked out by the outline of the paper. The normal force pushing back up, that's on B by the table. And then here we have the force of gravity on B by the earth, and that's a shorter one, kind of a lot smaller than this one over here because of the fact that it is a smaller box, or less massive box. And if we added those two together, they do equal the one going up as well. And what we see here is we have a force A on B, that's this one, and we have a force of B on A. And those two should be the same size. So that's your equal and opposite force pairs. Force on A on B is equal in magnitude and opposite direction of the force A on B. Same thing here, but we've got it moving in the horizontal direction. We've got constant velocity, so still no acceleration, meaning our force needs to equal 0, net force. And we're going to draw these boxes. Now they've done them a little bit differently. I'm trying to keep them in orientation of what they are. Here's box B. That's that diagram. Here's A. You can notice that the vectors are smaller for the weight and supporting force for A, the vertical ones. B is greater. Okay, so for B we have the normal force and the gravity in the vertical direction. Those two are equal. But in the horizontal direction, we have, to the right, we have the force of box A on box B. So on B by A, that's this one here. And then we have the force of, this is friction, kinetic friction because it's moving, right? Constant velocity. So friction, you can just call it friction if you want. I'll put the note here. This is friction. All right, and that's counteracting the motion of box B. So those two are equal there. Over on A, same difference. We have the normal force from the surface here on A by the by the force of that box. Then over here we have the normal force A on A by B. So that's that one. Going the other direction, we also have a little bit of friction. Smaller friction because it's a smaller box. So we've got a couple different forces. Let's go around this object and see for box A. We've got gravity, we've got the normal force. All right, as we go around it, we got this hand touching it, pushing it this way. That's what this is, a normal force from the hand on A by the finger, is what they're saying here. On the other side, over here, we've got this contact over here. Well, that box B is going to be pushing on box A. So that's the normal force A on B. Then, of course, we have a little bit of friction, where those two, the friction and the normal force from A on B, equal the force of the finger, and so there's no acceleration. And they don't really have that on there, so I'll put it there. It's those three. All right. Newton's third law, A on B is equal to B on A. Where's B on A is here? A on B is here. They are the same in opposite directions. Let's circle them. This one and that red one there. Those two are the same, indeed. Now here we have a different example where the box is accelerating to the left, or to the right, excuse me. And so for box B, which is this one here, this is A, we have a net force in to the right for both boxes. This one's a little bit bigger than the other one because it's more massive. All right. But we've got our forces. Forces on B. B has a hand touching it, the ground, A, and gravity. So we've got gravity, we've got the normal force from the ground, or the table, all right, up here and down. That one should be easy enough to do. Let's do the left-rights. To the right, we have the hand pushing it. That's this one. Kind of a lot. We got to make it a little bit bigger because we know we have some forces in the other direction, but this side to the right has to be bigger. We got the normal force of B on A, on B by A. All right, that's this one here. And then we have friction. So the normal force from this surface and then also friction. And those two added together need to be smaller than this one on the right. For box A, it's a similar idea. We've got the gravity going down. We've got the normal force from the table pointing up. And then we have, as we go around the box, we have the push from B on A. So on A by B, that's this one. That's the big one to the right. And then we have friction right here. Our force pair is on A by B, on B by A. Those two there are equal and opposite in direction. They are equal in magnitude and opposite in direction, even though this is accelerating. So now we have three examples. We have a not moving zero velocity example, we have a constant velocity example, and we have constant acceleration example. Newton's third law, the force pairs in these interactions are there in all three examples, as you can see. And I know I'm going through this kind of fast, but I want to make this a timely video. So you can pause, rewind, do what you need to do. So let's keep moving forward. We got some other interesting ones. This is really, it's interesting, but it's really the same as number 5. You don't really have any difference here. I mean, they're hooked together and they're being pulled instead of pushed, but there's not really much difference. So this example is going to be exactly the same as what you saw up in number 5. If you don't, it's in the opposite direction, right? No, it's going in the same direction. All right, but you have some differences. So let's kind of walk through this one. Vertical direction for both of them, we have gravity and we have the normal force from the table. Those two are equal in the vertical direction, no problem there. We got constant velocity, so that means the lefts need to equal the right, no acceleration. For box B, which is this one, and box A. For box B, we have tension in the rope on B by the rope. That's this way to the left. To the right is going to be this hook here. It's going to be the normal force B on B by A, and that's what that is, that little green one. And then we have friction on B by the ground. All right, so we've got this hook is being is pulling. A is kind of pulling it or holding on to it to keep B from moving to the left. So that's where you get the green one there. On A, we have the normal force and gravity in the vertical direction. We have kinetic friction or friction to the right. It's going to be sliding to the left. And what's pulling it to the left is the action of on A by B. So that's what's happening there. So box B is pulling box A. That's what that force is. And the other one is kinetic friction. They are equal in all directions. Therefore, we have no net force, no net force. But our force pair on B by A, that's this one, and on A by B is this little one here. Those two are the same and in opposite direction once again, even though these are hooked up differently. Okay, now we're going to change up things a little bit. We got the a magnetic force here. I'm going to do my best to kind of help this one out. Actually, you might have to skip this one. This is looking kind of crazy. And I may have to do this one from scratch. Yeah, let me do this one on the separate page. So bear with me. We may just do this one in class, actually. I'll try to squeeze it in the video. We're getting kind of long here anyway. Number 8, does the force the magnet exerts on the refrigerator compared to the force the refrigerator exerts on the magnet? All right, the force, which there are 3 of them with a magnet stuck on a fridge. The magnet exerts a force on the refrigerator is equal and opposite to the force of the refrigerator on the magnet. The magnet pushes the refrigerator left. The refrigerator pushes the magnet with an equal force to the right. The magnet pulls the refrigerator right. The refrigerator pulls the magnet left with equal force. The magnet pushes the refrigerator down, and the refrigerator pushes the magnet up with equal force. If you think about all of those different forces, so you've got a left, a up, and a down, or left, right, up, and down. You've got all 4 directions. The refrigerator is so much more massive that the magnet vertical forces are insignificant if you do these to scale. So this is a difference in the size. That's why the forces may be equal and opposite, but the size is different. All right, I'm not going to sort through this mess here with these 2 things. The important part to remember is with this refrigerator and magnet, same as the next couple of questions, is the massive size difference. All right, if you saw in the video, inertia is the missing piece. You have to pair Newton's first law, inertia, with Newton's third law to explain things like this. That don't really make sense because you're thinking if the if the magnet's pulling the refrigerator, that's crazy because it's so small. Shouldn't it move? Why doesn't it move? It doesn't move because it's so much more massive than the magnet. So in interactions where you have something that's very, very massive and something that's not so massive, you don't get equal. It doesn't feel the same. Think about yourself jumping. Jumping is a good example for this too. If you jump, you push off the ground and accelerate yourself upwards. Why doesn't the earth go down? The earth doesn't go down because your little push from jumping is insignificant towards the mass or changing the motion of the earth. There's kind of this age-old thought game that if everyone stood on one side of the earth in a big massive group and everybody jumped at the same time, could you change the motion of the earth? All right, think about how many people that would take to jump at the same time in order to even affect how massive the earth is. Same thing with the magnet and the refrigerator. This one we can go through. Number 9, how does the force on A on B. There's no force A on B and no force of B on A. This is in constant downward acceleration free fall. There is a net force down. The only forces acting on either of these blocks is the force of gravity. Now this is very interesting, and I'm going to do this demo in class next time and show this. But a mass on a spring scale, which I don't have here, else I would do it now. But if you watch it while it's hanging, there is, you'll see the force of gravity. But when you let it goes down to zero because there's nothing. They're both falling at the same rate. Everything falls at the same rate regardless of mass. Air resistance changes that a little bit, but you can see kind of the notes for what the demos could be, and I'll do the spring scale demo when we're in class again. But know that even though they're setting on top of each other, the forces are not, they're moving or accelerating. So they're both accelerating at the same rate, A and B, and there's no force. If you were to put a scale, like a bathroom scale, in between these two blocks and drop it along with them, falling in free fall, the scale would also read zero. I know it is kind of weird, but that's what you've got going on. This is why, if you've ever seen like skydivers where they strap people to their chest, if you've ever seen massive differences in size for those people, like let's say the skydiver instructor is a small person and the person that's doing the skydiving, which is strapped to the front of them, is a very large person. You may think, oh my gosh, that's asking for problems. That person's going to fall faster or anything like that, or you're going to feel the pull of that heavier person on the smaller person. That's not true. Once they jump out of the plane, even if they're connected, they're still falling at the same rate. So it's weightless. They're not attached to them. You don't feel them attached to you during that time. So the Earth and the person just standing on the Earth and the person on the Earth. This is a counterintuitive thing, but the Earth pulls on the person, and the person supported by the Earth is the same as if you do it from the perspective of the Earth, on the Earth by the person, and the normal force of the ground on the person as well. You standing on the Earth, when you stand on the Earth pulls you down, but you also pull the Earth up. Because of inertia, the Earth is so much more massive, that pulling force, the amount of force that's being pulled, you're pulling on the Earth gravitationally, is so small that it's insignificant. And the age-old question, which the diagrams are all messed up on this one, but this one was answered in the video. If you watch that, a force diagram for the Earth and the Moon, they are equal and opposite in direction. Again, that inertia question comes into play here for the force that the Earth exerts on the Moon comparing to the force that the Moon exerts on the Earth. Again, reiterating the fact that since the Earth is so much more massive, it still pulls on the Moon with the same amount, and the Moon pulls on the Earth with the same amount, as those are the same force, but the Earth obviously doesn't have an effect, or very little tiny effect. You see the effect on things that are not necessarily attached to the Earth, like tides or the water. All right, water is not necessarily attached, so the water gets pulled toward the Moon. This is why we have tides. And then when the Moon is on the other side or away from the that body of water, the water kind of drifts back toward its natural locations where it would be, right? So the Moon pulls water toward it, or out to sea, toward the Moon, based on that's how we get tides. All right, kind of a long video. I'm sorry about that. This was a long one, but hopefully this will help you out and get this thing done. We'll go over some of them as questions in class on Friday. Thanks.